So today I want to talk about these, how we'd go about determining whether it's working and whether it's working accurately. I'm going to split this into two sections. Firstly, I want to show you a device that I've been using since the 1980s to measure, but it has a few drawbacks. I'll show you the device and we'll discuss that first, and then we'll move on to a build of a much more modern device purchased from AliExpress. No sponsorship. Okay, so here's the device. It's based around a 7.4 series inverter. Well, this isn't the original that I built in the 1980s. It's the same circuit, but I have built it more recently because it was just getting old. So the basic idea of this guy is that it uses three inverters on this IC, so it's only half of the chip is actually used, and between the output of one inverter and the input of the other inverter we have a capacitor. Now I've made this so it's easily to change the cap. I currently have a 223 in there. I think you can go up to probably up to around 100 nanofarads and work just fine. Across each one of the inverters we have a variable resistor. Yeah, it's a 10k pot. It's a dual pot, so each one gets adjusted with the same resistance or thereabouts. Then we feed the output of the second inverter into the input of the third inverter, and then that is the actual output which comes here on this short wire. The crystal under test goes between the input and output of the first two inverters. Power supply, 5-volt power supply, and that's basically it. So the idea is that you put the crystalline test into the socket here, and then you have to slightly adjust the frequency using the pot to tune in to the specific resonant frequency of the crystal, and then we can measure the actual resonant frequency using an oscilloscope. So I'll set this up and then we can see it in action. Okay, so as I said, we need an oscilloscope for this, so I'll connect that up first. Hopefully we'll be able to see this. So this is the output. It comes directly out of the third inverter and ground. Power, so it needs 5-volt power supply. Let's start with an easy-ish crystal to measure. Standard crystal. Okay, so we'll pop him in. We have to adjust the we can adjust the pot until the circuit starts to resonate. Now this isn't the best scope. It actually is showing a really bad waveform. I think on a decent scope the waveform actually looks a lot better than this, but anyway, it's measuring it. So if we can see at the bottom here, I'll get out of the way, it's measuring at 4.2 megahertz, and it's actually a 4.19 megahertz crystal. If you can see that. So that's the easy one. Now, as I said, this has got some limitations, this device. It really doesn't go up very high in frequency in modern terms anyway. It was pretty good in the 1980s. In fact, it's exceptional in the 1980s, in my opinion. Anyway, so here we have, it's an 8.38 megahertz crystal. So we'll put this one in. And I don't really need to tune it for this one. So that's measuring as 8.41. We have, let's go a little bit lower than that. We have a 7.2 megahertz. Okay, 7.2. We have an 8 megahertz. And then the last one, no, so this is really going to be the upper limit of what this guy can do. This is a 16 megahertz. I'm not sure if this is going to work or not. Let's just try and tune. Not even sure if the leg's long enough to reach actually. No, I can't get it to work at that frequency. I have had it working in the past at 15 megahertz, but it's not working with a 16 megahertz crystal. So let me just see if I can find something in the high 14s, because it should work up to 15. Okay, I've found a 13.824 megahertz crystal here, but the legs are not long enough. So I've just attached a couple of loose wires into the pins here just to extend them. And then we hopefully, if we plug that in to there. $13.9, and that really is as high as I'll go. It will go up to 15, but it's a push. So that is the major limitation of this design, in my design anyway. In particular, on a piece of Ferro board, it will only go up to around 15 megahertz. If anybody's interested, I can supply the circuit diagram for this. Just put a comment in the comment section below. And also, if you'd like to subscribe to the channel, please, that's very helpful. So as part of this video, I'm going to make this kit. It's a 1 to 50 megahertz crystal oscillator frequency counter stroke meter. So let's go ahead and open it up and see what we've got. Okay. Can't get in. Okay, so what we got? We have 5 7-segment LED displays. We've got various resistors. Various diodes. various capacitors. An IC socket, an IC, crystal, power socket, 3-pin header, looks like a variable capacitor, trimming cap. We have a push button, and we have an S9018, which is a transistor. We have a 7550A, which I think is a voltage regulator, and an S9014 is another transistor, and the PCB, of course. So if we have a look at the IC here, it is a PIC 16F628A. So before I start actually putting the kit together, what I usually do is bend the legs on the axial components, like the resistors, diodes, anything that needs to have the legs bended. So for that, I have one of these leg bending tools available from many places. I think this one was actually around just over £1 from CPC, I believe. So the way I use this is basically I just look at the PCB to see what the spacing is for the particular design, and I think we're going to go for the second size up for the main resistors. The diodes will have to be the first size, so we can go ahead and start bending those. We can do multiples in one go, not a problem. We're going to actually have to go to the third size up because they don't actually fit in the space. And when we have loads banded together, we can literally lay them in. Over. Okay. So then what I do, I've got a PCB holding device here, so we can actually mount the PCB into this guy. Something like that. So I start with the, no, actually let's put it the right way around. Oh. That's better. So I tend to start with the components that are flattest to the board first. So being resistors, diodes, small capacitors, and then we just go up in size, gradually building the layers. So we can go ahead and start installing some of these 1K resistors to start with. Okay, we can flip the board over and solder those guys in. Yeah, snip the legs off. So I do normally, before building one of these kits or during the course of building the kit, actually check all the components. So I must admit I've forgotten to do that right now. So I'm just going to check these 1K resistors, and then from that point forward we can start checking them before we put them in the board. So let's just quickly check these. Nine nine one, 981, 989, 985, 980, 981, that's here we go, 986, 987. We'll just test the ones that I haven't actually put in the board yet. So we've got 100k, which is correct, 10k, which is correct, and 10k, which is correct. Okay, let's put those in. So we've got 100k going there. We've got 10k going there. And a 10k going there. Let's go ahead and put the diodes in quickly. Check those first, of course. Let's go into diode range. Point 6, 0.6, 0.6, 0.6. Lovely. Okay. Put those in. So diodes are polarity conscious. They have a black band, and that lines up on the board. And the last one is going there. Okay, let's flip that over and solder those in. Okay, snip those off. This one. So next, I'll just check the capacitors, make sure they're the values that they're supposed to be. So that's 1N. 100N. 28 picofarad. It's supposed to be 22, but I think that's close enough. 22. 33, that one. I do. Maybe I need to zero my leads. Better. 24. Okay. We'll say that they're okay. So there's a 22 going there, and a 22 going there. And I don't see a space for the other one, so we'll put that to one side with the resistor. Okay. Let's go ahead and solder those in. Get the legs off. So next up, we'll mount the transistors and voltage regulator. We'll just test the transistors first. Can't test the voltage regulator, I don't really have anything to test that with, but we can certainly do the transistors. NPN bipolar transistor. NPN bipolar transistor. Right, that's the 9014, which goes in there. And that is the 9018, which goes there. And that is the 7550, which goes in there. Okay, solder those in. And trim the legs off. Okay, next up I will do the IC socket. That goes in, there's a notch on the IC socket that lines up with the notch on the silk screen. Some bent pins going on there somewhere. There he is. Okay, okay. So what I normally do with these is flip it over, and I'll just tack a couple of legs on to hold it in place. Make sure that I haven't put it in the wrong way around, which I have. So we'll have to take that out. And have another go at that. Okay. solder him in. Check it's in the right way around this time, yeah. Good. Hmm. Looks good. Okay, next up, we'll do the trimmer capacitor. Again, I'm going to have to hold that in and tack it. Tricky. Power plug. Crystal. Switch. So that just leaves me with this little header. And 7-segment displays. Bent legs. Just go ahead and solder all those in now. And then snip all those little ladies off. Good, complete. Let's just pop the chip in. Going it the correct way round, of course, which is that way. Oh, bent leg. Temporarily misplaced my leg straightener, so I'll have to do it the old-fashioned way. No problem. Should be good enough, hopefully. Good. Okay. So here we have the finished article. Now, I have looked and I don't actually have a jack that fits this socket here for the DC power. But what I do have is a JST type battery connector socket and plug, and that will fit perfectly onto the board here, and then I can just power it from whatever. So I'm just going to go ahead and solder that on there. Like that. Now, perfect. Okay, let's find some power. Back in a moment. So I've actually got two lithium batteries here connected in series, so around 8 volts ish. So that should actually do quite nicely. So let's power this up for the first time together. That's actually the other way around. So it would appear that the polarity of this is non-standard, so I'm just going to make an adapter just to swap the polarity over. I like to keep it so I can reuse it as necessary. So I'll just see. The red one is going on the left, that way around. Let's get a bit of heat shrink. Okay. So hopefully now. Good. Now that's not coming up very well on camera at all. In fact, you can't see it in the slightest. Okay, I'm just going to go and make a lens. Okay, so I've made a dirty lens. Hopefully, let's have a look. Oh yes, okay. So now we can see what it's actually saying. So the whole reason that I actually built this kit was so I could actually test some crystals. Now I've got various crystals kicking around of various frequencies. Now in the past, back in the day, I made a tester for crystals, back in the 80s, 1980s that is. But that thing is quite limited. It really only goes up to around 14, 15 megahertz maximum. And I'm going to show you that in a while, or I may have already shown it to you, depends. So I've got a 20 megahertz crystal here. So let's just see what this thing is actually saying. It's not the easiest to operate, to be honest. Okay, 20.0062. Now I have got so I've already tested this one. This is exactly spot on. So this is a 4.19304 megahertz crystal. It's very interesting. So now I know this one is correct. I've used it already and I've tested it already. And this thing is kind of all over the place, isn't it? Oh, is it settled down? No, I would say that's not very good. Now, I did manage actually to find some kind of instruction manual for this, and I think the reason that they give you this extra 22 picofarad cap is to try to overcome this issue where it doesn't read lower frequencies very well or very accurately. So I'm going to just do a bit more research. So after some investigation, it would appear that the idea is to tag this extra cap in parallel with the existing one. So that's this one right here. I believe it's the top one. So let's just try that. I'll just literally just tack it on. Okay. And wow, that's actually stopped it from working totally. Hmm. Okay, what about the 20 megahertz? Is that still working or not? Yes. Okay. Okay, let's take that back off. Let's just try it across the other 22 PF cap. Nope. Interesting. Okay. Let's take it off again. Oh, hang on. Maybe I didn't have it on. Let's just try that again. Ah, okay. That is better. Right. Okay, I'm gonna put that on properly. Okay, so I've attached that on to the place that I think it should be now. Soldered it on nicely. It's not touching anything. It's in a good place. So that's actually on the second 22 picofarad cap down. So it's the one in there's a 102 and then 222 picofarad, and it's the one in the middle. I'm just going to go ahead and actually put this heat shrink on here before I have an accident with that as well. Okay, so let's try this again. Okay, that was instant that time, much better. So let's try 20 megahertz crystal. Ah, we seem to have run in a problem that it won't measure a 20 megahertz crystal. Hmm. Okay. What else have we got? Hmm. Okay. 7 megahertz. Yep. 8.38. $25. No, that's very interesting. Okay. Just going to lift that leg off again. 25. Yes. Four. No. Okay, so it appears that we've run into quite a major shortfall with this guy. I'm just going to consult the book. After wasting far too much time messing around with the fact that it was very slow reading the lower frequency crystals, I think I've actually found the problem. It turned out that the 1N cap, the original 1N cap, was actually quite a bit too high. I looked back at the original footage that I shot when I was measuring the capacitance, and it was about I think it was 1030 picofarad. So I found another 1N cap which is actually spot on 1N. I put that in, and now we've got the 4.19 megahertz crystal. It's quite quick. And we've got a 30 megahertz crystal, which is pretty good. And just to show you guys, I've got the original cap here, the one that I took out, the one that was supplied. Let's just 0 the meter. And that's coming up as, yeah, 1022 picofarad. So when they're asking you to add an extra 22 picofarad, I'm already got that in my circuit. So that's assumably that's why I was having the problem. So now I've got my 22 picofarads are spot on. I've actually replaced those with my devices, which are actually spot on 22 picofarad, and I've now got 100N in the circuit as well. Sorry, 1000 picofarad, 1 nanofarad. They're all spot on those values. And now it works just fine. So I have managed to find a manual for a unit which is very similar to the one that I have. This is actually on Banggood's website. I'll put a link in the description. I'm not sure if it's identical to the unit I have. I purchased mine from AliExpress, but it seems to be very similar anyway. So it has the circuit diagram here. So we can see that the two capacitors in question, the two 22 picofarad caps, are actually marked as 20 on the diagram. Whether that has any impact, I'm not entirely sure. Could do. But the one that I had a problem with was this one, C6, the 1 nanofarad. So just so you have that information. It does go on to explain how the decimal place works. It does go on to the hidden features, which are listed here. So basically, in short, it's got a function where you can add an offset to the frequency, you can subtract an offset from the frequency, you can zero. Now, to start with, when I first started using this, I did have a bit of a measurement error, and having zeroed it, it has pretty much eliminated that error, so that's well worth doing. There are a couple of things here which I'm not sure that my one has. So it goes, so this is power save, so you can have power saving on or off, which basically disables the screen if there's no change in frequency for a certain period of time, and it will reactivate the screen on a change of frequency. And then there's a table, so you can actually select predefined measurement frequencies. Just out of interest, for information, this crystal is actually 4.194304 and measures it as 41951. The last thing I want to show you with relation to measuring crystals with this is I've actually made up a small set of clip leads here because this thing is actually really quite awkward to use, and also I have lots of crystals with very short legs and you really can't get them in there. So I've made up a clip lead. Let's just to show you that it doesn't really affect the accuracy that much. So here I have an 8.38 megahertz crystal, which I will try and plug in. It's very difficult. Okay, 83878. Okay, let's plug in the clip leads. Eight 3876. So as you can see, at 8 megahertz, it makes absolutely hardly any difference whatsoever. I've got some various other crystals here with short legs, so that's 25 megahertz. 25 megahertz. Let's pick one at random. 24. 23,996. 25. 24,999. Something a bit different. 20. 13.824. 13.825. So this guy is actually, even with the clip leads, I think it's actually more accurate, to be honest. I don't quite know how that works, but there you go. It's working